All right, today we're talking about proving geometric relationships. Essential question, how can you use a flowchart to prove a mathematical statement? So we're going to learn how to use what's called a flowchart proof and also a paragraph proof to prove geometric relationships. All right, so what we're going to start off with is with a flowchart, and that is kind of what like it sounds like. Flowchart is just boxes and arrows to show the flow or the direction of this logical argument. Okay, and we're going to start off with proving this right angles congruence theorem. Right, and it says basically that all right angles are congruent. All right, so here's our first example, which is that right angles theorem, and we're just going to kind of create this chart using what's given to us. So they kind of give us a drawing here that kind of confirms or draws, it illustrates this given statement. So we always start with our given statement, angle 1 and angle 2 are right angles. All right, so we're going to kind of put that in a box. All right, now we take this idea, take that statement, and we're going to write given underneath that. And then we're going to take that statement and we're going to say, what is that? We're going to ask ourselves, I should say, what does that mean? Okay, well, if I know angle 1 is a right angle, that means that the measure of angle 1 is equal to 90 degrees. And same thing with angle 2. If angle 2 is a right angle, I can kind of interpret that or translate that into saying, well, that means the measure of angle 2 is 90 degrees. All right, so our statement goes inside the rectangle, and then the reason goes underneath that. And so I can go from this statement to this statement because that's the definition of a right angle. Okay, and we want to show our end result is going to be, we want to reach this conclusion that angle 1 must be congruent to angle 2. Okay, so now if I know that angle 1 is 90 degrees and angle 2 is 90 degrees, the next kind of logical thing to say then is that, well, if they're both 90 degrees, that must mean that the measure of angle 1 has to equal the measure of angle 2, because they're both 90. Right? Now, we would call this the transitive property. Transitive property. Now I'm going to abbreviate transitive property of equality. Right. Now, because I know that they're both the same angle measure, I can now say that they are congruent. That must mean that angle 1 is congruent to angle 2, because that's how we define congruence. If they're the same shape, which they're both angles, they both have the same size, the angle measurement, the 90 degrees, then they must be congruent. So that would be definition of congruent angles. Okay. Now, this is just another kind of way to model a proof. We use a two-column proof. That's the most popular one, where we have our statements on one side and our reasons on the other side. Okay. And so if this flowchart kind of thinking helps you, by all means, write that out. So what we're going to do now, because to use a flowchart proof to write two-column proof, so we would just translate this into a standard two-column proof. So I'm just going to copy that. Give me 1 second. All right, so here you go. Like magic, I translated this flowchart into a two-column proof. It would be the same thing. Both of them are considered mathematically appropriate, I guess, if you want to think of it that way. But like I said before, this is kind of the more common standard way of writing a proof. But if the flowchart helps you, And we just want to kind of expose you to that. All right, here's another flow chart to kind of for you to look at and just get an idea of what a little more practice using a flow chart. Now remember that this upside down capital T, that means perpendicular. Okay, so I know that segment AB is perpendicular to segment BC and segment DC is perpendicular to BC. That's our given statement. Okay, then we would say that must mean that angle B and we'll also say and angle C are right angles. Okay. If these lines are perpendicular, then these two have to be 90-degree angles. And because they're both 90-degree angles, the theorem that we just got through looking at, I know that angle B is congruent to angle C. And that theorem was called the right angles theorem. That said all right angles are congruent. Okay, I'm gonna leave it up to you to draw the, to translate this into a 2-column proof. Okay, remember that your statements are on the left and your reasons are on the right. All right, we got 2 more theorems that we're going to kind of add into our toolbox that we can use in our reasons when we're doing these kind of proofs. And the first one is the congruent supplements theorem. That just means that if you know that an angle 1 is supplementary to an angle 2, and you know 2 and 3 are supplementary, then that means 1 and 3 have to be congruent, because they're going to add up to the same numbers. 2.5 says the congruent complements theorem. Same idea. I know 4 and 5 add up to 90, and I know 5 and 6 have to add up to 90, so that means 4 and 6 have to be congruent. All right, so that brings us to example number 2. All right, and so that's the congruent supplements theorem. We're going to actually kind of prove that. So I'm going to walk you through this 2-column proof, and I'm going to leave it up to you to translate the 2-column proof into a flow chart. All right, so let's get started. They're telling us that 1 and 2 are supplementary, and we also know that 2 and 3 are supplementary. We want to arrive at the conclusion that angle 1 is congruent to angle 3. So of course, remember, we start back with our givens. Right? And then we take that statement and we translate it. Well, if they're supplementary, that must mean that their angle, the sum of the angles, add up to 180 degrees. And we call that the definition of supplementary angles. That's what it means. We're just translating it into another sentence so we can use it. All right. Well, since they both add up to 180, would it not make sense that they're equal to each other? So we combine the 2 sentences, and when we kind of do that, that is called the transitive property. All right. And then if I look at this statement, I want to get at angle 1 being congruent to angle 3. But I got these angle 2's that are kind of on both sides of the equation. So what I can do is I can actually take those 2 out and still have this equality because angle 2 is on both sides. That's our subtraction property. So if I take away the angle 2 from both sides, I'd get the measure of angle 1 is equal to the measure of angle 3. And I can do that because of the subtraction property. So measure of angle 1 is equal to the measure of angle 3. Right? And if they're equal in measure, and they're talking about 2 angles here, angle 1 and angle 3, that must mean that they're congruent. So we would call that definition of congruent angles. Okay? Now again, like I said before, I'm going to leave it up to you to translate this into a flowchart proof. This is just practice exposing you to looking at different types of visuals for proofs. All right, we're going to introduce real quick two more tools for our proofs. First one's a postulate. It's called the linear pair postulate. If two angles form a linear pair, then they are supplementary. That's kind of like a duh, because that is part of the definition of a linear pair, is that their angle measure is 180 degrees. All right, next thing is vertical angles theorem, and we're going to say that vertical angles are congruent. And your vertical angles, remember, that's angle 1 and angle 3. Those are the ones that are kind of across from each other, kind of making like a mirror reflection. So 2 and 4 would be a pair of vertical angles, and again 1 and 3 would be a pair of vertical angles. All right, and now we're going to introduce what's called a paragraph proof. All right, again, this is just a different version of the two-column proof, but you can actually write it out in sentence form. That's what a paragraph proof is. All right, so real quick, next example, I'm going to give you the vertical angles congruence theorem. I'm giving you kind of a real-life example. And we're going to show you a paragraph proof just so you can see what it looks like. Again, it's just something, if that's kind of how your thought process works, if you write it out in sentences and that works for you, that's great. We can translate that into a two-column proof if you need to. So we're starting off with this picture here. I got these, I guess, runways that intersect, and they form these vertical angles. 5 and 7 would be the vertical angles. And we want to prove that vertical angles are actually congruent. So what we would do is, in a paragraph form, we would say angle 5 and angle 7 are vertical angles formed by intersecting lines. I can say that because that's what was given to me. All right. As shown in the diagram, 5 and 6 are a linear pair, and angle 6 and angle 7 are a linear pair as well. Then by the linear pair postulate, the one we just looked at before this example, angle 5 and angle 6 are supplementary, and angle 6 and angle 7 are supplementary. So, by the congruent supplements theorem, angle 5 is congruent to angle 7. Okay? So now what we're going to do is I'm going to translate that into a two-column proof. And so, here we go. Here's what it looks like. 5 and 7 are vertical angles. That's given. Then we would say angle 5 and angle 6 are a linear pair. And same thing for angle 6 and angle 7. Kind of shortcut my writing. And that would be definition of a linear pair. And then we kind of put in parentheses as shown in the diagram. All right, and then let's see where we're at. 5 and 6 are a linear pair. Then by the linear pair postulate, 5 and 6 are supplementary, and 6 and 7 are supplementary. So we would say angle 5 and angle 6 are supplementary, and angle 6 and angle 7 are supplementary. Which means if we look back at our proof, we would say by the linear pair postulate. So that's that. And then looking at this, we're down to our last sentence, which says angle 5 is congruent to angle 7. And we would call that the congruent supplements theorem. All right, here's the last example we're going to look at. We want to solve for the value of x, find the value of x, and we have this diagram here. This would be kind of our paragraph proof. Angle TPS and angle QP are vertical angles. We know that because of the way the picture is drawn. by that vertical angles theorem, we know that the angles are congruent. So we're going to use that to come up with an equation. Because these are vertical, I know that they're equal. I can use some algebra to solve for x. So let's do that. Okay? And then we want to justify our steps. So I know that the measure of angle TPS is equal to the measure of angle QPR. And my reason? Definition of congruent angles. Okay, because I know that, I'm going to use the actual measurements, which would be the 148 is equal to 3x plus 1. And that would be just substitution. Okay, now I really don't need the parentheses. I can kind of ignore those, since I don't have any multiplication or division associated with the parentheses. All right, and then I need to get the x by itself, so I would need to subtract 1 from both sides. So that ends up giving me 147 is equal to 3x. And that would be my subtraction property of equality. Then I would divide by 3. So 147 divided by 3 gives me 49. And that would be the division property, again, of equality. And that's what it asks for, find the value of x. So that would be my proof statement, I guess, if you want to look at it as a proof.